Hi, I'm Raghu and welcome back to another session in the series of programming a Raspberry Pi Pico using Python. One of the requirements of a project is to turn on or turn off the light based on the ambient light condition. To detect the ambient light level, we use an LDR. LDR stands for light dependent resistor. It's a special kind of resistor whose resistance changes with a change in the intensity of light. An LDR has two pins. It can be connected in any circuit in the same way that a resistor is connected. The LDR pins have no polarity and the pins can be interchanged. And this is the schematic representation of an LDR. Let's now connect an LDR to a circuit. If you are using the Y0 boards, then you can connect the LDR to the Pico using a 3-pin RMC wire. Take out a 3-pin RMC wire. On the Y0 Pico board, find the 3-pin RMC connector marked as A0. Plug in the 3-pin wire to this connector. On the push button LDR buzzer PCB, find the RMC connector marked as LDR. Plug in the other side of the 3-pin RMC wire into this connection. If you are not using the Y0 boards, then you have to connect the LDR to a Pico as per the schematic diagram shown here. The middle of the resistor bridge will be connected to A0 of the Raspberry Pi Pico. That's it. We can now move on to write code for the LDR. The first two lines are import statements as usual. Observe that I'm importing two classes, pin and ADC, from the machine module. Python allows you to import multiple classes from a module by adding a comma between the classes. In the next line, we define a variable called LDR of class ADC. The LDR is connected to GPIO26. Just like the previous tutorial, here too I am defining an LED variable. Now you might be wondering why I didn't use the pin class even for the LDR. Isn't that also connected to a GPIO pin? Well, that's because the pin class is meant for digital pins only. That is, those pins which can either have a digital high or a digital low. GPIO26 is an analog pin. It is typically connected to devices that produce analog values. I'll explain more about analog and ADC after I complete this code. For now, just remember this. You can provide any value between 0 and 3.3 volts to a Pico's ADC pin. The first line after the while true statement is ldr.read_u16. What this method does is that it reads the voltage on the GPIO pin, which is 26 in this case, and converts it to a 16-bit number. So we get a value between 0 and 65535. If the voltage is 3.3 volts, then the number will be 65535. If the voltage is 0 volts, then the number will be 0. In case of the LDR, if the ambient light is very low, then the voltage will be close to 0. In case the ambient light is very high, then the voltage will be close to 3.3 volts. Using the if block, we turn on the LED when the ambient light is less than half the maximum. We turn it off when it is more than half. We also print the value of the analog read on the console. That's it. Save the Python file and connect the Pico to your computer. If you show a bright light into the LDR, then Pico's onboard LED turns off. If you block the LDR, then the LED turns on. Now that's great. We got our LDR circuit to work. Let me now give a short explanation about analog signals, digital signals, and ADC. When we wrote code for the basic I/O, I already explained a little about digital signals. Digital signals can just have one of two values, low or high. Unlike digital signals, analog signals can have any value. They are not limited by ones and zeros. And the truth is, everything around us is actually analog. The light we see, the sound we hear, the temperature, vibrations, etc. All of these have energy levels which could be any value. As an illustration, I'd like to show the waveform of a simple sound. The energy levels looks like this. This is how the sound energy looks like when plotted on an XY graph. The x-axis shows time and the y-axis shows energy. When I capture the sound over time, the graph moves like this. So to summarize, an analog signal can have any value at a given time or a range of time. However, a digital signal can only have one of two values, high or low. Since most of the things around us produce analog energy, when a sensor converts this analog energy to electrical energy, the result will also be analog. However, when we work with microcontrollers, we need digital values to process data. Therefore, we need to convert from analog to digital. To do this, we use analog to digital converters. The technology, techniques and working principles of ADCs are way beyond the scope of this tutorial. It is enough if we know that an ADC converts an analog value to a digital value. The accuracy of an ADC is measured in terms of n-bit resolution. For example, a 10-bit ADC can have a value between 0 and 1024. Now let's take the example of a 10-bit ADC which is capable of reading voltages up to 5 volts. 0 volts will be converted to a digital value of 0. 5 volts will be converted to 1023. Digital value of 1 means 5 divided by 1023, which translates to 4.88 millivolts. So 4.88 is the minimum resolution of a 10-bit ADC which works at a VCC of 5 volts. While most of the modern day microcontrollers have a built-in ADC, this is not always necessary. For example, the Raspberry Pi itself does not have an ADC built into it. Coming back to the Raspberry Pi Pico, it has a total of 4 ADC ports. Out of these 4, 3 of them are exposed as GPIO pins 26, 27 and 28. The last one is not exposed and is connected to an internal temperature sensor. The last ADC can be accessed by passing the parameter 4 to the ADC class. So we could say temp sensor equals ADC bracket 4. We can read this value and convert it to a temperature by using the information given in the Raspberry Pi Pico's datasheet. So that's it. Let's move on to another topic. Hope you enjoyed this session and have got a good understanding of the concepts that we learned here. So let's move on to the next session in this series of programming a Raspberry Pi Pico using Python. So see you soon.